So this video is going to be about light, sound, and for light, the frequency and wavelength determine the color. So over here I'm going to write all the colors of the rainbow. There's the there's the acronym RGBIV. This stands for red, orange, yellow, green, blue, indigo, and violet. And red is the longest wavelength and low frequency. And then violet down here is the shortest wavelength and highest frequency. So as I'm changing the wavelength, I'm changing the frequency, and that's changing the color of the light. The second little bullet about that is going to be brightness. And brightness is the amplitude. So the bigger the amplitude, the brighter the light. Light always travels at the speed of light. So its velocity is 3 times 10 to the 8th meters per second, and that's constant. Light always travels at that speed. And then our last little bullet that I'm going to mention is light can travel through a vacuum. Okay, for sound, frequency and wavelength determine pitch. Okay, low frequency and long wavelength is low pitch, and high frequency and short wavelength is high pitch. And one way to think about that is piccolo is a really short instrument. It's going to have short wavelengths. It's going to be higher pitch. A trombone is a much longer instrument. It's going to have longer wavelengths. It's going to be lower pitch. Amplitude is loudness. So a bigger amplitude is going to be a louder wave. Speed of sound varies with temperature, but I'm going to say it's about 340 meters per second. So sound is pretty fast, but it's way slower than light. Light is 300 million meters per second, whereas sound is 340 meters per second. And we see that with a lightning strike. We see the lightning, and it takes time for the thunder to get to us. It's about 5 seconds per mile. All right. And one thing I'm going to say is sound needs a material medium. So it can't travel through a vacuum. So if you're out in space, light can get through space. Light gets from the sun to the earth, okay? But sound cannot. There's no sound in space because there's no air molecules to transfer the sound. Our last one is going to be electromagnetic radiation. And we'll make a note for this. It uses electric and magnetic waves, electric and magnetic fields as a medium. They can travel through a vacuum. And and they always travel at the speed of light. And we have the electromagnetic spectrum. Draw it here. This is going to be long wavelength over here. And this is going to be short wavelength. This is low frequency and high frequency. Right in the middle of this band, we're going to put light. Light is just this little narrow band of electromagnetic radiation. And it would be red on this side where there's long wavelength, and violet would be on the right side where there's short wavelength. Right below red, we have a type of radiation that means below red. It's infrared. Just below that are microwaves. And just below that are radio waves. So radio waves have really long wavelengths and low frequencies. Now, if I go just above violet, we get to ultraviolet. And above ultraviolet are X-rays. And above X-rays are gamma rays. So light is just one of many types of electromagnetic radiation. The only thing special about light is that we can see it. And remember, all of these always travel at the speed of light. So you might get a question where you need the speed of an X-ray. You need to know that the speed of an X-ray is the speed of light, which is this 3 × 10⁸. And that's something you should be writing on your reference table.